Okay, photonic, quantum, and MEMS. Any idea what these fields have in common? Yeah, nice. Yeah, traditionally, they had pretty bad tools. So I've been making chips for 15 years, and when I started doing chips, I tried all the tools. I was not able to even draw bends on like proprietary tools. So we basically started GDSFactory 6 years ago, and since then we have reached over 3 million downloads. We have 100 developers working on it, and we have over 500K downloads in the last 5 months. I work in many companies, Intel, HP, SciQuantum, and Google. I was part of this Google Skywater GF180 open sourcing of the PDK, so you can actually pip install Sky130 or pip install GF180. So basically, the issue I found is that existing tools were not able to do the job, especially for these new technologies, such as quantum and photonics, as MEMS. The vendors were very slow to adapt. So we had tape-outs, we had to show progress, and the tools were not at the level that they had to be. So we basically took the blue pill, and we never regret looking back. Also, all the traditional proprietary tools have pretty weird languages. We wanted to do everything in Python. We had many companies from the beginning jump into these workflows. We had regular meetings between all these companies, which was kind of like, we had a big community from the beginning, starting to develop features together and develop PDKs together. Since then, we have developed 9 open source PDKs. So we just released a new quantum PDK like a couple of weeks ago. As part of Google, we made this Skywater and Global Foundries. And we have many photonics PDKs, because photonics is a very new technology, and it's very suitable for programmatic design. And then we also, now that we have a company behind it as well, we can also develop proprietary PDKs. This was one of the main difficulties that we found as an open source project. We didn't have an entity to sign NDAs, so we couldn't provide users with proprietary PDKs, which are also very important. And we should all be aware that proprietary PDKs need to be part of the picture of a big project like GDSFactory. How does it compare with other tools? I mean, we're not allowed to show benchmark with proprietary tools, but we hear all the time it's very much faster. I can show here a benchmark with GDSPy, which is very common in academia. Compared to GDSFactory, we can get up to 200 times faster. Why is that? It's because GDSFactory is using the KLayout C++ backend. So we have Python usability, and we have C++ speed. How does it work? You can describe your circuits in Python. You can describe your circuits, your netlist in YAML. And you can synthesize from Python to GDS, but you can also you can run a simulation, because in all these new fields, it's important to be able to do TCAD simulations, RF simulations, electromagnetic simulations. So directly from the Python code, we can drive the simulations and even do an optimization loop. So to summarize, we can be up to 200 times faster. We have a library of components that are open source. So we have over 250 components open source. And we have over 25 PDKs available. And we integrate with all the other tools, thanks to the Python interfaces. We also have a company now behind it, so we also offer like graphical user interface tools, verification tools, as well as data validation, like to store all your chips and be able to store all your data. The model that we follow is very similar to what Tom showed with Precision Innovation. So we have the GDSFactory, which is open source, and we have also the GDSFactory Plus. We keep all the solvers open source, we keep all the plugins open source, and we maintain, as many PDKs are open source, we maintain them open source. But we also have the proprietary side where we maintain the GUIs, the data management extensions, the lithography extensions, as well as the PDKs under NDA. So some of the success stories. So this is a student from a university. He was able to tape out just in a few weeks a full chip. This was actually tested. This is done in Skywater. It was tested at NIST at cryo, and they were able to characterize a PDK at cryo temperatures, which is very important for quantum. We have developed like finite element solver. So this is a solver called FEMWell, where we can do not only device level, but also chip level FEM simulations. This is for heat. We have developed PALAS. This is developed by the AWS Quantum team, where you can do RF simulations at very large scale. This will be a replacement of HFFS. We have done TCAD simulations with DevSim. And there's all, in the same way that you cannot expect to beat your computer at chess, you cannot beat your computer at chip design, so it's better that we accept that. So we prove adjoint optimization. We've done like advanced routing techniques where we can do like very complicated routing. You can see this is a tensor core multiplier, so you can see how fast it routes. We have done a microservice architecture where we can go from digital to analog to photonics and RF. And you can also interface with the quantum tools. So we also develop, this is like Vahid is here too. He developed this when he was a postdoc at the Max Planck Institute. Basically an assistant that helps you, I don't know if you saw it in the beginning, but they give you a menu of different circuits, like a switch, different things. And then you can actually choose the wavelengths or the resonance frequencies that you want to get. And it will give you all the way to the schematic as well. Oh, sorry. It will give you a schematic as well as the full circuit. Oh, sorry, let me go back. And it will be able to run a circuit simulation. So this is the schematic. It gives you the GDS layout. And then we use an open source circuit simulator for RF that will simulate the S parameters. And you will see them here at the bottom. So this is full circuit from layout to simulation. We can do hundreds of these simulations in parallel to estimate yield on the circuits. And what we are looking for help next is to expand into analog. So we are looking into SPICE support, same with microwave. We want to increase the open source. We would like to have an open source standards and library. There's some students who have developed this. We're talking with them to see if they want to open source it. And we would like to expand the support for more PDKs, especially the open ones, and be able to add reference circuits for people to get started. And I don't know if I have a quick demo if I have time, but basically, I can show basically how you go from Python into GDS. I wanted to say hello, orconf, and then basically you save, automatically see it. So it's a very easy way to describe your parametric cells. And then you can go all the way to like complex circuits. So I can create a circuit like top 5. I can just easily like add elements here, like just add a ring single. I can route them together. Let me show you the GDS so you see what we're looking here. So you can see 2 rings here. So these rings are filters and they have resonance frequencies. I can expose the ports. You can actually move the circuit even after you place it, and the route will automatically follow, and then I can turn it into a simulation. So this is simulating the frequency response of this chip. And once you're happy with the frequency response of the chip, you can actually add like a die, because you need to basically package it. And then you can create a route to the right. And then a route to the left. Let me create a route here, left. And this will give you like a full circle in just a few seconds. So now it's ready for package. Then the last thing you'll be able to do like DRC, and then you're ready for tape-out.
Thank you very much. Are there any questions?
Does the DSC complete?
Yeah. Yeah, it did. I think it didn't have any errors, but yeah, we have other chips with examples with errors. Yeah, you can also do LVS and also connectivity checks, because a lot of times you do complicated routing and then you can overlap things that you're not supposed to overlap. Yeah.
Hello. I have one question about FIDO, the tool you just showed. I was just wondering whether you can only simulate a subset of circuits, or you can basically simulate everything that is on the PDK for that. Andre?
Yeah, like usually you are using RAG, so it's basically retrieve augmented generation. So it's basically prompting. So it has aware of what it has in the PDK. You can also provide a few of reference examples where you have a prompt and the GDS. And when the components in the PDK have models, which is where we're spending a lot of time doing, you can actually use the models to simulate the whole circuit. Something that we are looking into expanding now is that we've proven this works for photonics. We want to prove this works for quantum as well as analog. And then that's where we are building these EM solvers to provide models for all these gates of these PDKs. So we can do full circuit. And the last thing I think it will be nice to teach Fido how to do physics, basically in a way like you give them figure of merit and then let them optimize. And this is very similar to, I don't know if you have seen the documentary of DeepMind, where basically they start training it with video games and they go to like very complicated like protein folding. They were able to solve problems that no human was able to solve before. So that's what the ultimate goal would be.
Okay, thanks.
Thank you, Joaquin.
Thank you.